I started on this road back in 2010 when I was at MIT working on side channel attacks on cloud computing and how to steal information from those computers that you're not supposed to trust. And that got me thinking, how can we trust a computer that we don't own, that is somewhere out there, controlled by someone we've never seen, and is running our code and producing output that's sent back to us? And I realized that zero-knowledge proofs, which were back then a theoretical curiosity and fascinating technique, but not on anyone's radar for practicality, I realized that this could, in principle, solve the problem if someone could prove to you that they have run the correct code for you. And moreover, if you actually change them, then you can reason about an ongoing computation consisting of multiple steps, maybe from different parties, that preserves some ongoing property. So with this in mind, I applied to the National Science Foundation for some funding to pursue this direction. And the answer we got was basically, this will probably never be practical, but if it ever were practical, then it could change the world. So here are a few bucks. So with that, we set out, my then student Alessandro Chiesa and me, to explore this notion, and we had a series of papers defining this notion of ZK-SNARKs, which distill the requisite properties of zero-knowledge proofs that you would need in these kind of applications, and proof-carrying data, which is the idea of chaining them together. And we started the collaboration with Eli Ben-Sasson and subsequently with Madars at MIT, Madars Virza, to actually implement these ZK-SNARKs. Along the way, a new generation of techniques based on QAPs came along, which provided another approach complementing the PCP-based approach that Eli was leading. And we used these to build a series of prototypes that show that these abstract ideas are actually practical. We actually were able to have a generic compiler that can take any C program and compile it into a new one that can verify itself and produce a succinct proof, a few hundred bytes, checkable in a few milliseconds, that would convince you that the program ran correctly, even if it was on the cloud or on hardware provided by the cheapest bidder. So we were very happy about that, and then we started thinking, what kind of C programs would we actually plug into this machinery? And that was around 2013. And these were just the days when Bitcoin became popular. People realized that, hey, blockchains are cool. And they were also starting to realize that actually blockchains are not private. They are revealing all of their transactions. We heard of that group over in Johns Hopkins that was also looking at that and actually had an approach for solving that, the zero-coin protocol, that sort of provides a private version of Bitcoin, but not with all the functionality that you would want, and wasn't fast enough, proofs were too large. And it turns out that the machinery that we had, and we were just so eager to find some nice use cases for, was exactly the missing ingredient in the protocol. So we got together in 2013, and we started scheming and finding out how to compose the ingredients and how to build a new protocol that uses those SNARKs in a way that is tailored for that application. And that actually worked out. Within a few months, we had the first draft. And in 2014, we presented this at an important security conference, but important for academia. And it turns out that that is not quite enough to make an impact in the real world, because we thought we had solved Bitcoin's privacy problem, and we were waiting for the world to beat a path to our door and use it. And after waiting for a while, we realized that we may need to be more proactive, and that the extra effort required to take academic code and making something that you would trust your mother to put her life savings in. That's not something that can be justified within academic research, and it's not something that was on anyone else's radar. So we reached out to Zuko and to List Authority because of their excellent reputation designing cryptographic protocols for the real world. And together with the Johns Hopkins team, consisting of Matt Green, Ian Mears, and Christina Garman, we set up the Zcash company as the vehicle to create what would become Zcash on top of that zero cash protocol that we have published academically. That took nearly 2 years of additional engineering effort, a lot of review, finding and fixing bugs, learning about all the extra challenges needed to make things usable and trustworthy. In October 2016, we actually shipped the code, and that was, I'm proud and happy to say, the most boring launch of my life, because it actually worked. It keeps working to this day. Then here we are, finding ways to make people use it.